Hello everyone, welcome to the lecture series of finite element analysis. In the today's lecture, we will discuss about determination of stiffness matrix and stress for plane truss element. This is Dr. Manoj Kumbhalkar. So first of all, what is plane truss? Trusses are very common type of structure used in steel buildings and bridges. Example, railway bridges, transmission towers. This could be entirely in a plain 2D truss or special 3D trusses. So this is an example of plane truss. So the plane truss is made with the help of the straight members and it is connected at the joint. So if you see the definition of plane truss, a truss is the type of structure that consists of all straight members connected together with pin joints connected only at the ends of the members. So in the given figure you can also see that all these truss members contain the elemental straight members. So that straight members are joined here if at point A. These 3 straight members, 4 straight members are joined at point A. At point C again that 4 straight members are joined and the complete joint is made as a truss. The main examples of the trusses are railway bridges, transmission towers. These are the example of trusses. You have already studied that trusses in the engineering mechanics. So the plane truss having different bridge structures. So here some pictorial views of the bridge structures. So here you can see that bridge is made with the help of that straight members and joint at some point. This is again the second example of the bridge. Here that rectangular portion is converted to the triangular by adding one straight member here. So all the bridge structure is made with the help of the straight member. Then this is the finite element analysis of that bridge structure. This next example for the trusses are nothing but the towers. So the 7 wonders, the Eiffel Tower is one of the wonders from total 7 wonders in the world. So that tower is made with the help of all the straight members. If you zoom that portion, you can see here that Eiffel Tower is made with the help of that all steel straight members, and if you are again zoom that portion, you can see here this is the truss member and it is made with the help of that straight members and joint at some points, and the complete joint will made a complete Eiffel Tower. This is again the 3D model as well as the mesh model of one of the tower. Here you can see that this is the elemental bar element. The elemental bar element joint at some points can made a complete tower. These are again some examples of the towers which is used for the electricity transmission. Now there is need to understand the local and global coordinates over the truss. A truss element have different orientation and every node have 2 degrees of freedom in x and y direction. In the given figure you can see that this is an element having nodes 1 and 2, as every 1D bar element having 2 nodes, that is 1 and 2. So the truss is also a 1D bar element, but the displacement of node, if we studied about the local coordinate, the displacement of node 1 is q1 dash and displacement of node 2 will be q2 dash, but this is the local displacement of node 1 and 2. And if we studied about the global displacement of the node 1 and 2, as each node in the plane truss having 2 degrees of freedom, so the q1 dash is distributed as q1x and q1y, and q2 dash is distributed in q2x and q2y. We can write q1x as 1 and q1y as q2. Likewise, Q2x as Q3 and Q2y as Q4. By considering the orientation of truss element, a local and global coordinates are defined. A 2D truss element is shown in figure in both local and global coordinates. So, how can we write the local displacement vectors? The local displacement vectors for the node 1 and 2 are Q1 dash and Q2 dash, or U1 dash or U2 dash. So, the global displacement vector is nothing but the distribution of local displacement vector. The Q1 dash is distributed as Q1 and Q2, that is in x and y direction, and Q2 dash is distributed as Q3 and Q4. We can also write it in the form of U1, U2, U3, U4. The local displacement Q dash is related to global displacement as sum of the projections of global displacement Q1 and Q2. So, in the given figure, if you can say this is the local coordinate having node number 1 and node number 2. The local coordinate defines that the deformation only in the x direction, that is in the direction of element. But in the global displacement, we can see that the node number 1 can be deformed in x direction and in y direction, that is Q1 and Q2. So, the Q1 will be equals to in the form of angle, this is angle theta. So, therefore, Q1 dash will be Q1 cos theta and plus Q2 sin theta. Likewise, Q2 dash will be equals to Q3 sin theta and Q3 cos theta plus Q4 sin theta. So, this is the local this is the equation for the conversion of local displacement matrix into the global displacement matrix. So, we can write that equation in the form of matrix, that is Q1 dash Q2 dash, which is local displacement matrix, will be equals to, we can write this equation in the form of matrix. So, for Q1 cos theta, so here is Q1 cos theta, then Q2 sin theta, here is sin theta. There is no Q3 term in the first equation, therefore it is 0. There is no Q4 term in the equation, therefore it is 0. Likewise, in the Q2 dash, Q1 term is 0, Q1 is not available, Q2 is 0, Q3 cos theta plus Q4 sin theta. So, accordingly, the matrix can be formed as 4 by 2. Multiply it with the local displacement matrix vectors, that is Q1, Q2, Q3, Q4. At this stage, the direction cosines L and M are introduced, as L is equals to cos theta and M is equals to sin theta. So, that above matrix can be replaced as Q1 dash Q2 dash is equals to L M 0 0 0 0 L M, multiply it with Q1, Q2, Q3, Q4. So, that L and M are referred as direction cosines, that will be equals to L is equals to cos theta and M is equals to sin theta. So, that complete matrix can be written as the global displacement vector equals to the transformation matrix into the the local displacement vector is equals to the transformation matrix into the global displacement vector. So, what is the transformation matrix then? It is nothing but L M 0 0 and 0 0 L M. This is nothing but a transformation matrix. So, now how to calculation for direction cosines? How to calculate that direction cosines? So, direction cosines L and M can be calculated from the element geometry. So, this is an element having equivalent length LE and the node 1 having coordinate x1 y1 and node 2 having coordinate x2 y2. So, what will be that term? That horizontal will be x2 minus x1 and vertical term will be y2 minus y1, and this is an angle theta made with the horizontal line. So, the the direction cosines L, which is already we discussed in the previous slide, L is equals to cos theta. So, what is cos theta? It is nothing but the adjacent side, that is x2 minus x1 divided by LE, and M is equals to sin theta, which will be equals to the opposite side, that is y2 minus y1 divided by LE. So, if you want to solve the numerical of plane truss with the help of angle, you can use L is equals to cos theta, M is equals to sin theta. And if you want to solve the numerical with the help of coordinate, you can use L is equals to x2 minus x1 divided by LE and M is equals to y2 minus y1 divided by LE. So, equivalent length of the element is obtained from the coordinates of the node, that is under root of x2 minus x1 square plus y2 minus y1 square. Now, how to determine the element stiffness matrix for truss? So, the element stiffness matrix for 1D bar element is K is equals to AE by L 1 minus 1 minus 1 1, which has already been discussed in the previous lecture. So, the element stiffness matrix for truss is obtained as the element stiffness matrix KE is equals to the transpose of transformation matrix into the element stiffness matrix for 1D bar element into the transformation matrix again. So, write down the matrices, the transpose of the stiffness matrix, that is LM00 and 00LM. Sorry, here M is required instead of 0. AE by L 1 minus 1 minus 1 1 into the transformation matrix, that is LM00 00LM. So, if you multiply all these matrices, you will get a standard stiffness matrix for a plane truss, which is very simple to remember, that is AE by L, which is common term as that of 1D bar element, multiply with, instead of 1 minus 1 minus 1 1, here now the 4 by 4 matrix is there. So, here it is L square LM LM M square. Then the adjacent elements are minus L square minus LM minus LM minus M square. Then the diagonal elements are minus L square minus LM minus LM minus M square, and this again adjacent elements are L square LM LM M square. So, this is a standard stiffness matrix for plane truss element. Then how to determine the stresses in the truss element? So, again we will use the basic equation for the stress in the element to determine the stress in the element. So, which is nothing but E into B into Q. So, E is the modulus of elasticity, B is the strain displacement matrix, which is nothing but 1 by LE minus 1 1 into the transformation matrix into Q, that is global displacement vectors, that is Q1, Q2, Q3, Q4. So, if you put the transformation matrix here LM 0 0 0 0 LM and multiply it with the all elements, you will get E by LE minus L minus M L M into Q1, Q2, Q3, Q4. So, this is the standard equation to find out the stresses in plane truss. So, thank you very much. Any question about plane truss element, write in the comment box, and if you satisfied with the video, please click on like. Also subscribe the channel for more informative videos. So, thank you very much.